So just 1 minute left and then we'll have a look at the answer. Seconds. All right, let's have a look at this guy. So, math, please. What's the first part? A1, is it? Part A? Part 1? Part A.
There's a big an elastic band of mass 5 times 10 to the power 3 kg. Is stretched vertically downwards from a fixed point by 20 cm. Using an average force of 1.5 Newton.
Sorry, 1 second. 1.5 newtons. 20 cm.
It is then released, causing it to be projected vertically upwards. What is meant by elastic behavior of a solid?
Sorry, it's just to give you all the information, and the first part is, so what's elastic behavior of a solid? So is this like A part 1? Yeah. So elastic behavior, this means...
this is part A.
Oh, there's like part B then? Yeah, okay. Yeah, but is it just A and then B, or is it A1, A2?
The information is the big question.
Oh, I see, sorry, so like the A isn't really here. Yeah, I get you now. The A is like down here. Okay. No, that's important because you want to get your information straight. So what is meant by elastic behavior? So this is when the... What's the word? Hang on. Oh, perturbed. What is it? I want a fancy academic word. Not distorted, not disfigured. Oh, what's it called when you change the shape of it? Deformed, thank you. Deformed. Goodness, I forgot it. I'm not sleeping enough. Right. When a deforming force, when a material is deformed and a restoring force proportional to the displacement. When a material is deformed and a restoring force proportional to the displacement results, then we say the material is elastic.
What if I just say it returns to its original shape once force is removed?
That's nice. Well, we'll check the marking scheme in a second. I.e., elastic materials obey Hooke's law. Siva, give me the marking scheme answer and tell me I got my full marks, please.
Returns to original shape length when force is removed.
Yeah, that's...
Yes.
I wrote without breaking.
What did you say? What was your answer?
How much a material can be deformed without
That is called something else. That's called the, for goodness sake, tensile strength. Thank you. What is wrong with me today? Tensile strength. So your answer is okay. Yours is for tensile strength, though. What did you say, Kim?
I don't know.
Okay. What did you say, Matt?
The ability of changing shape without changing the initial shape.
No. No marks for you. Sorry. George?
The ability of an object that can stretch and still regain its original shape.
Marks for you. Okay. All right, good. Okay. Tough break, Matt. Okay. B. You didn't write anything, Kim. You left it blank?
Yeah.
Are you sure? You're not being shy?
No, I don't try to know
Okay. Okay. Matt, B, please.
B1.
B1, thank you.
How much work is done in stretching the elastic band?
Ah, we're back to our picture.
Give an appropriate unit with your answer.
Okay. So they want the work done. So work is force by distance. What was the force?
1.5.
And the distance was 0.2.
Yes.
So what's that, 0.3?
No.
0.3 joules. How many marks was that now, Matt?
3.
No.
Yeah.
No. 3 marks. Are you sure?
Yeah.
And Siba, is this the right answer in the marking scheme?
Yeah.
So you get 3 marks for multiplying 2 numbers.
It
Okay.
says 0.30.
Okay, so 0.300 if we want to be 3 significant figures.
They give marks to the units also.
The what? Give what?
The units. Correct unit.
Unit.
Yeah, but you always. Oh, never mind. Okay.
It's not
Never mind. Never mind. Part 2, Matt.
If the transfer of this energy to the initial kinetic energy of the rubber band is only 80% efficient, how much initial kinetic energy does the rubber band have?
So what you've done is you've pulled it down and released. Although they're being very unclear here because I thought the story was somebody pulls the rubber band down. So there's no initial velocity because it's at rest at the beginning. Now all of a sudden they're talking about initial velocity.
No, initial kind of.
Yeah, which is the same thing. Anyways, the language is not so clear, but the idea is this. You pull it, you give it energy, you release it and it starts to move. So they want to know what is the kinetic energy at the equilibrium rather than at the center of its motion. In other words, this energy here converts into kinetic. And what are they asking for? How much kinetic? How much kinetic?
How much initial kinetic?
Okay. Sorry, maybe I misheard the question. Siba, could you, or no, who has it open? Matt, can you read the part about the story at the beginning?
An elastic band of mass 5 times
Mhm.
10 to the power of negative 3 kg is stretched vertically downwards from a fixed point by...
Pause. Okay. Sorry, pause. So it's a rubber band, it's stretched vertically downwards. Okay, continue.
Using an average force of 1.5 Newton,
Okay, so the man is pulling it down with 1.3 newtons, okay?
it is then released, causing it to be projected vertically upwards.
So it's released. So at the beginning, it's at rest. Okay, so there's no initial kinetic energy. The kinetic energy doesn't appear until it moves up to its equilibrium. Okay.
So it's 0?
It says if the transfer of this energy to the initial kinetic...
Yeah, no, go on. What about the transfer, did it say?
If the transfer of this energy to the initial kinetic energy of the rubber band is only 80% efficient.
Yeah. Okay, we'll continue. My only problem with that sentence is the word initial. There is no initial kinetic energy. I think they meant a different word, like equilibrium, I suspect. Anyways, no matter. So we want to get 80% of this, basically, because you have the formula. Efficiency would be the energy out, which is the kinetic, over the energy in, which is the work done, times 100%. So 80% equals kinetic energy over 0.3 times 100%. So when you solve this, you get 0.24 joules. Is that the answer? And how many marks was that one? How was this 2 and the last one was 3? I don't get that. Okay, next part, Matt, please.
What is the initial speed of the elastic band?
Boring. A half mv squared equals 0.24. So that means v squared equals 0.48. Now we know the m, don't we? It's, what is it? 5
Times.
5 times 75
negative 3, and then we have to take a square root as well. So what did we get for the v?
9.8.
9.8? It's pretty big.
Yeah.
Yeah? Okay. Meters per second. Right, part 4?
Assuming no air resistance, to what maximum height above its starting position will the elastic band reach?
Now, this is a problem because it's our English. So can I just draw the picture here? Look. So the boy pulled it down to here, right? And what were we told this distance was? 20 centimeters. Now, if we take this as the starting point, then how much does it rise when it gets to the maximum point? To here? 40. Okay. But if you take this as the starting point, then how much do we say it rises?
20.
I really, really, really want it to be 40, because if the boy pulls it down to here and you release it, this is the start. But because of the previous question, he's making it sound like this is the start. So, tell me, Siba, is it 20 or 40?
What, the answer?
Yeah.
4.9 meters.
4.9? I must have misheard the question. Can you read the question to me again, please, Matt?
Assuming no air resistance,
Yeah.
to what maximum height above its starting position will the elastic band reach?
And you said the answer is 4.9.
It uses the kinetic energy equals to potential energy.
That's what
Yes. I tell you why I'm wrong here. Well, maybe this is a better experience for you. What is making me wrong here? Why am I wrong? Why can't I do what I just did here? Or is that what you guys did?
I didn't think that far.
Say again?
I didn't think that far.
Okay.
Yeah.
The reason I'm wrong here, does anyone want to tell me? Nobody can see why? The reason I'm wrong here is because the efficiency is 80%. So the process of pulling this down is not 100% efficient. So it means it doesn't quite have this symmetric movement here. Some of the energy was lost, so it won't quite do the full 20. That's my point. Because the 80% efficiency, the amplitude is actually less than 20 centimeters. That's the reason why. Thank you. So, you're right. You're absolutely right. The marking scheme said the best thing to do, if we take this as the starting position, here it has only potential energy, and then up here it has only potential energy, but it's a different type of potential. This is the energy stored in the rubber, whereas this is the energy due to gravity. So all that happens is the potential energy you stored here, which, what did we say was 2.8? No, 0.28, wasn't it? 2.4. That energy gets converted into potential gravity energy. In both cases, the speed here is 0 and 0, so we don't need to consider the kinetic. Now that's if I take this as the starting point. If I take this as the starting point, then it's a different answer. Now, because of what you said, he said kinetic energy equals potential energy. So it's making it sound like he's taken this as the starting point. So I'll do both answers to show you. If you do it the way I think it should be done, which is starting here, you have 0.24 equals m. What was the mass? 5 times 10 to the g h. So h is 0.24 over 5 times 10 to the minus 3 times 9.81. However, if you take the start as being in the middle, what energy do you have here? Kinetic. And if you take this as the beginning and the ground, then it has no potential. So the height this time would be 0.24 equals mgh. It's actually the same thing. The only difference is, oh, you get the same answer. Yeah? Same thing, isn't it? Nice, okay. Okay, that's fine. Same answer. Nice, okay. So, in both cases, what's the h here? 4.9? No. 4.9 meters. 4.9 meters. The boy pulls it down 20 centimeters and it moves 4.9 meters. I can't believe that. I'm sorry. I don't believe that. If you type this in, you get 4.9. You pull it down 20 centimeters and it moves 5 meters.
Maybe there's like
The super rubber band. You realise for that to be true, the rubber band has to be, you know, like 10 meters long. Yeah. So clearly the numbers chosen for this question aren't realistic numbers. You know, I would have expected 4.9 centimeters, not 4.9 meters. All right, what's the next part?
C.
C, great.
The last 20% of the initial work that goes towards heating the elastic band.
Right, sorry, so that's 0.06 joules. That was the lost amount of energy.
It has a specific heat capacity of 1250.
Yeah.
If you have no answer to part B1, assume the work done is 0.4.
Okay, but we do have an answer. 0.3 minus 0.24. So we have to account for our missing 0.06. This is the lost energy. Yeah? So, they want the change in temperature, is it? Yeah. So you have M, is it 10 to the minus 3? Was it? Yeah. M, C, delta theta equals 0.06. So the extra increase in temperature will be 0.06 over 5 times 10 to the minus 3 times 1250. What's that number, Matt, when you're ready?
0.0096.
0.0096 Celsius warmer. And Siba, what's the answer in the marking scheme? Is it that?
It's in Kelvin.
They used Kelvin? What did they get in Kelvin? No, don't use Kelvin. Oh, sorry, they wrote Kelvin here. Sorry, no, excuse me. Never mind. Fine, it's the same thing, Kelvin, yeah. The same thing? Yeah, okay. Is there another part?
Yes.
Yeah.
D?
D.
Okay.
If a student wanted to investigate the Young modulus for the elastic band, describe the measurements which would be needed, the instruments which could be used to measure them, and how they could be used to find the Young modulus.
Okay. So, okay, here's the experiment. You have your rubber band. And what you could do, you could attach some different weights to it. Okay, so you need to have a box of weights. And this is the rubber band. and this is a hanging weight, or weights. And then, of course, you need some way to measure. So you measure, you can measure here, you can call this L, and this is F. And F equals the weight, which in this case equals mg. And what you do is you vary m. So in other words, you put on small weights, then you put bigger weights, and then you put bigger weights. So if you change the m, that means you've varied the f, and then you measure the L, measure the length that you get. So then you make a graph. Oh, sorry, no, then you calculate, then you have to calculate stress. Stress is extension over, stress is force over area, and strain, extension over length. Now, can you calculate the extension? Yeah, of course you can, because you measure the length at the beginning, and then when you put on the weights, you measure the extension here. The only problem is the stress. It's force over area. Now, do you know the force? Yeah, but do you know the area? No, so you need something to measure the area. Does anybody know how you can measure the area of a string? How do you measure the area of like a little string? Like, you want to measure the area of this.
The vernier clamp?
Yeah.
Wait, you're talking about the width or?
No, you're right. Werner something or other. I have a different name for it, but I know that name for it. I don't know if you've ever seen them. They look like a clamp. And what you do is you put the string inside of it, and then you clamp it, you turn it until it shuts. And then you can measure on it the thickness. And then once you have that, you can get the area. It is called something like a micrometer. There's many names for it, to calculate the area. Right, so once you do all that wonderful stuff, you can make your graph finally. So which do we put on the x and which do we put on the y? So which is the thing that we're changing, the stress or the strain? Which here is the x and which here is the y? Which is the x and which is the y? Which is the thing you change and which is the thing you observe?
You change stress.
You change, so that goes on the x, that goes on the y, okay? So that's stress, that's strain. You draw your graph and you calculate, you find, oh goodness, you find m, and then finally, Young's modulus is stress over strain, so in this case it'd be 1 over m. Oh, good heavens. How many marks for that, Matt? 6, yeah. Siba, is that the last part?
Yeah.
Can you finish us off by reading out the marking scheme for this?
Measure thickness with vernier calipers or the micrometer scorecard.
Okay, stop. That's 1 mark. Is that 1 mark?
Says you. No,
Oh.
2.
That's 2 marks.
Measure thickness is 1, and with vernier caliper it's 1.
Okay.
Then measure width, not measure area.
Okay.
Measure length, that's 1 mark. With the ruler or meter rule, that's another mark.
I never said what to measure it with. Measure L with meter stick. Okay, that's 1 mark. Go on.
Because in the question it says, and the instruments which could be used to measure length.
Yeah, I forgot about that. Sorry, go on, yeah.
Measure extended length.
Yeah.
Use thickness time width to find area.
Use thickness times width to find area. Oh my goodness, they want you to calculate the area. So you can just use pi r squared. So I forgot about that. This is disgraceful.
Describe, use a formula Ym equals stress over strain with clear process for finding stress and strain, or Ym equals F times L over E times L.
I'm missing a marker. I only have 5 here. 1, 2, 3, 4, 5. Where's the extra mark?
The width, not area. Measure the width.
Well, we measured, yeah, so I have 2 marks for measuring the width and the area,
Yeah.
yeah. And then 1 mark for measuring the length. And then is it 1 mark for saying it's a meter stick?
Yeah.
Oh, so then it's 2 marks there, okay. And then 1 mark for calculating the area?
Yeah.
And then 1 mark for the stress strain formula?
Yeah.
So what is that on the slope? Yeah, that.
It's an arrow. Find them. I don't like that one. How many marks do you think you would have gotten yourself? 2 for you? Yeah, yeah. 3. Okay. What did you leave out?
The area.
How to measure the thickness? And you knew how to measure the thickness, though. Did you? You would have gotten that. Did anybody else know about that?
I didn't know exactly, but I just knew what to use to measure the thickness.
Yeah, it's Fern or something or other. I always call it by the other name, micrometer. I have one at home, actually. Sorry, and just before you go, I know we're probably, just before you go, just a little bit of English. Because you just said something that reminded me. These are 2 different words with 2 different meanings. What's this one here? How would you say that? Micrometer. And how do you say this? No. Yes, micrometer. Yes, micrometer. So this one here is, this is 1 word. Wait, don't go. I know you're hungry. Look. Micrometer for this guy, and this one is micrometer. They're 2 different words. And this one here measures small distances. How small? Well, about this size. Yeah, so this is a new word for you, isn't it?
No, just I say it.
Oh no, but they're not this. Yeah, yeah,
I know they were different.
yeah, yeah. You need to
I thought
say.
it was just like a different accent.
No, it's not. No, you have to say micrometer. You have to say micrometer. Yeah. Okay. Right. That's a bit of grammar for you. English is weird. The reason, Matt, is this here means meter as in length, but this here means meter as in to measure. Yeah, ruler's a strange word. I think it's an old word. You see, these are more recent English words.
Some says rule.
Yeah?
R-U-L.
Ah, yeah. Rule versus ruler. I think this is maybe a difference between the UK and Ireland, or maybe US and Ireland. In Ireland, we call them rulers as the noun. But in other countries, they might call them a rule as the noun. What would you say?
For the ruler?
The thing you use to draw
I don't
lines.
know if you could call it rule.
What do you call it?
Ruler.
Yeah. All right.